All right, today we're looking at graphing two variable inequalities, x and y. We're going to see these most of the time in standard form, okay? All right, so these two variable inequalities are going to be in standard form most of the time, like we see to the right over here. But instead of an equal sign, we're going to be one of those inequalities that we learned about in the early part of the year, those alligator mouths, okay? So how many possible are there? There's 4 possible ones. There's a couple greater thans and there's a couple less thans. So we have our greater thans. Whoops. Greater than or greater than equal to. Okay. The other ones are the less thans, a regular less than or a less than equal to. So those are the 4 possibilities we can get in our linear inequalities. All right, so from this, those inequalities are going to determine how our graph looks. So one thing those inequalities tell us is the type of boundary line it will be. So there's 2 types of boundaries possible. So we're going to look at boundary lines. All right, so we could have a solid boundary or a dash boundary. All right, so a solid boundary, those are just a solid normal old line that we've been graphing for a while. Okay, so they could be an increasing line, decreasing, or our horizontal or verticals. Okay, the dashed lines are the same thing, but instead of a solid line, okay, instead of having a solid line like that, it's actually a dash. So what I'm gonna do is actually erase parts of this line. So that's a dash line there. Again, they could go up or down, be decreasing as well. So make sure there is no connection there. Those are dash lines. Now what makes these is the solid ones. These are called the equal to's. So when you have an equal to inequality, for example, a less than equal to or a greater than equal to, they're going to create this solid boundary. So when we graph the line, it will be a solid line. The way I remember this is if you have a solid line in your inequality, like the equal to bar, it's going to make a solid line graph. Okay, down here, these are the not equal to's. The not equal to. And that's just our regular old less than or greater than. See, there's no equal to part to it, so we can't have a solid boundary. When we graph these, we're going to see that the points on the dash line are not solutions. Okay, where our points on the solid lines will be exact solutions. Again, the points on the solid line are solutions. It's because it's actually the equal to part of the equation. We're going to see if we were to plug points in on the dash line, it's going to create an inequality that's almost true. Something like 7 is greater than 7. All right, let's talk about shading now. All right, the shading will also be determined based on the inequality that we see in the equation. But before you determine how it's going to be shaded, the best thing to do is to get it into slope-intercept form. So, in slope-intercept form, you're going to look at shading here. So, the one way to do that is to get the y by itself first. Once you get the y by itself first, again, that's just our slope-intercept form. Then determine the shading. Don't do it before. If you're in standard form, let's say you're looking at something in this form up here, don't determine the shading until you get the y by itself. Okay, once you do that, if you see it's a greater than, It's one of those greater thans. Remember, the greater than, it could be a regular greater than or greater than equal to. So this is very important that you actually know that this symbol means greater than. Okay, no longer looking at the alligator and it's eating the bigger number. That won't help you in shading. Okay, the alligator won't help you in shading. You have to know that these are greater than signs, and when you see a greater than, you'll be shading above the boundary. Because everything greater than will be above the boundary. Whether it's a dash or a solid line. So we're gonna shade the graph above it. And I'll show you a little bit. Now the other way is the less thans. Okay, if we have a less than, and that's our regular less than or the less than equal to, we'll be shading these below. The boundary. Shading is another way of saying we're going to color in the solution region. We're going to color in part of the graph. So that's the one way of doing it. In my opinion, it's the best way. There is another way to determine shading that I want to add to our notes. And that is using a test point. I'm going to add that in right here. And the easiest test point, the easiest numbers to plug in for X and Y are always 0. So we can use a test point, and we're going to see one of two things could happen. You can get a true statement or a false statement. If it's true, that means that part of the graph should be shaded. So if we test 0, 0, the origin, and we see it's a true statement in the equation, that part of the graph should be shaded, should be colored in. If it's false, though, we're going to shade the other part of the graph. Again, the best way, in my opinion, really is to get to slope-intercept form, because you're going to see we have to do this anyways to make it graph ready. All right, for steps for graphing, these are a review from our graphing slope-intercept form from a few weeks ago. Make these graphable by converting to slope-intercept. Get the y by itself. Okay, maybe that will help. Remember, get y by itself. Okay. Now, when you're in that process, though, we are dealing with now inequalities. So you have to remember back to that special rule about inequalities. You guys remember? Flip if we dividing or multiplying. So if you end up having to multiply, maybe you're going to fraction bus with a negative number for some reason. Most of the time, though, you will divide. And you divide by a negative number, you have to remember to make sure to flip the inequality or rotate it. Make it face the other way. Okay, if you forget to do that, think about what we just talked about above. What would it affect on your graph? Yeah, that's right. What side of the boundary we shade? If you forget to flip something, you will shade the wrong part of the graph. Okay? Ouch. If you're using the slope-intercept way. The backup way would be the test points. All right, after you convert it, what did we learn to do? Plot first. Yeah. Plot the y-intercepts. Plot your y-intercept, your b value, not the base, but the y-intercept. I had to say it, sorry, Cruz. All right, now if you notice, I underlined the letter what here? M. Because what we're going to do here? Yeah, we're going to move to another point using the slope ratio. Very good. On a graph, someone said we have to remember this is our rise over run. So we plot a point and then we rise and run to a new one. Now that's all review, but now the extra things we'll add in here is the boundaries and shading. So the next thing we have to remember is draw the correct boundary line, which is determined by our inequality. We know that if it's an equal to, we'll have a solid boundary, or if it's a not equal to, just a regular old inequality, we'll have a dash boundary. And we're going to put those through those 2 points. The last thing we do, using our inequality in slope-intercept form, we're going to do shade. We're going to look at the inequality to determine what half of the graph to shade, either above or below the boundary. You can also use the test point too. All right, let's use these steps to do the first example. Now notice example 1 and 2, one of them's harder than the other. This one's harder because it's not in what? It's not graph ready. It's not slope intercept ready here. This one is. This one's already ready to go. Before we graph it, let's go ahead and identify what kind of graph it should be. Like, we look at the inequality here. We have the y by itself. What should it look like? What's the boundary look like? Good. It should be a dash line because there's no equal to. And we should be shading where? It's greater than, so above. Above. All right, let's go ahead and go through the steps. Plot the b, so positive 5, 0, 5. There's our y-intercept. And then our slope here, our y-intercept was 0, 5. Our slope is -2. That means do what? Down 2 and over 1. Down 2 and over 1. Now we're going to use our straight edge and draw a dashed line through those points. All right, I've moved to many points there with my slope, down 2 to the right 1. Now I'm going to get my straight edge out. I'm really actually grabbing a ruler and putting it on the iPad. And I'm going to graph a dashed line through these points as long as it registers. Let's hope. Didn't do it earlier. That is not a great line, but I'm going to fix it with my eraser. All right, now I've kind of made it a little bit better. Put my arrowheads on the end there. We see a dash line boundary there. All right, next, last thing to do, we have our dash line. What's next? Shading. Now, imagine that you're on this line. Okay, if I stand there, I won't fall off. But if I stand right there, what's going to happen? That's kind of gruesome. I'll fall down, but I don't think I'll die. Okay, so obviously there's only one place you can stand on. So think about standing on this line, anywhere on this line, and we have to shade above, greater than above your head. So everything above this line. Okay, so let me get rid of some of these drawings. And everything above my head there will be shaded. So I'm going to go ahead and shade to the right of the line or above the line here. Right and above. Yeah, I guess it's both. And there's your inequality graph. Now on a test, you might freak out. You're like, I don't know if Mr. Van Meter could see if that's a dash line or not. So if you're worried about it, you can always label it. Okay, you can always say, hey, this is a dash line actually. Because sometimes people shade really dark and you can't really tell if I'm looking at a solid boundary or a dash boundary. So if it helps, you can list it. All right, let's go to the next one. All right, example 2 is not graph ready. It's not ready to go here. But you could use intercepts. If you wanted to graph using your X and Y intercepts, you could do that. Plug in zeros and find those points. But you're going to see that one of our intercepts is actually off of the chart over here. So we couldn't do it in this example. So our only thing to do, the best thing to do, is solve for Y. Get the Y by itself. So what's my first step to get the Y by itself? Do the opposite, subtract X from both sides. So now we have negative 4y. Still have the less than equal to. Put the x first, negative x, and then plus 8. Last thing to do here, we're going to see something come into play. We're going to do what?
Divide by negative 4.
Divide by negative 4. And right there someone said, gotta flip the sign. We divide by a negative, we have to flip the inequality the other direction. Okay, so we'll still have y, but now it will be greater than equal to. And we go over here to simplify our slope, negative x over negative 4. Don't forget. Very good. Don't forget that's a negative 1 right there. Negative over negative becomes a positive 1/4 of x. And then 8 divided by negative 4 minus 2. All right, let's go ahead and graph now before Samuel falls asleep on us back there. All right, so we're going to again plot the B. He's got it down. He's good. Negative 2, 0, negative 2. And we're going to move how? Up 1 over 4. Up 1 to the right 4. Up 1 to the right 4. If you couldn't do that on the graph, could you go backwards? Yeah. You do everything opposite. Instead of going up, go down. Instead of going right, go left. So down 1 and left 4 would be right there. Okay, now we talk about the inequality here. So that's two things that tell us there. It's going to tell us the boundary is what? It's going to be a solid boundary. And we're going to shade where? Above. It's a greater than again, so we'll be shading above. All right, so let's draw the line. Now I can use my technology here. Don't have to worry about a dash line. All right, so there's our boundary, our solid boundary, and now we're going to shade this above. So start shading everything above the line. Stay within the lines. Do not go over. Yeah, well, think about this goes this way forever and up forever and right forever. All of these values that I'm trying to cover here and beyond are all solutions. All solutions. They would all make the inequality up here true. And we're going to practice that here in a second. Let me finish shading. So before we move on, let's look at these bottom two graphs. And I want to talk about solutions because that's what we shade. We shade these graphs to show possible solutions and make these inequalities true. Everything in the purple region here, and both of them would make these inequalities true. But the boundaries are different. This one's dashed, this one's a solid. So we have to remember, solid lines, these points I have on here, would make the inequality true. These are actually not solutions on the left graph. So let's label this the solution region. Okay, whether we're looking at this graph or that graph, all those shaded region are solutions. Any point would be true. All right, but what's not solutions are the ones on the dashed line or over here. These are not solutions if they're not shaded, and as well as these points. Now let's see why. Okay, so let's choose one of these points over here. Let's do that one right there. What point is that? 2, 1. Because we will ask you sometimes to list possible solutions. Owen? Possible solutions. So if you think that's a solution on the dash line there, what is that, 2, 1?
Yeah.
We could test it in the inequality above. So our y value is 1, our x is 2. So 1 is greater than negative 2 times the x value of 2 plus 5. So what's negative 2 times 2? Negative 4. That's negative 4 plus 5. What's that equal?
1. Oh no.
1.
Oh yeah, that's right.
1. 1. Is 1 greater than 1?
No, it's equal.
No, it's equal to. This is why we don't include the points on the dash line, because they make these almost true inequalities. This is false. Not a solution. Okay, so anytime the points are on the dash line, like we wrote above, they are not solutions. But these ones over here are solutions. They're exact solutions.
What?
Okay, so if we chose that point to test in the other equation, that would be negative 4, negative 3. And we're going to go plug it in up here and test the solution. X is negative 4 minus 4 times the y value, negative 3. It's supposed to be less than or equal to 8. So what's negative 4 times negative 3?
12.
Positive 12. Positive 12 right there. What's negative 4 plus 12? 8. It's 8. Is 8 less than or equal to 8?
Yeah.
Yes. This is why we include the points on a solid line, but we don't include the points on the dash line. All right, go ahead and practice on the next 2, or actually go ahead and do on the next 4 problems here. Do the next 4 problems here. And what I want you to do for each of these also underneath is list 3 possible solutions. All right, there is the 4 graphs. I'll zoom in on each of them. Let's look at the first one here, example 3.
How did you do that?
So we're looking at, how did I graph this? Well, first of all, I plotted my y-intercept negative 1. So 0, negative 1 is right there. And then my slope is down 1 to the right 2. Down 1 to the right 2 would put me right there. All right, so then I go back to my equation and go, how am I going to draw this line? Well, this is not equal to, so we remember this is going to be a dashed line. Not equal to. Any point on the dashed line is not a solution. And then we also see that it's a greater than. So we were going to shade above. And that's what we see on our graph here. It's shaded above. 3 possible solutions. All right. Well, what about this point right there? 0, 0. Is that a solution? Yeah, it's in the solution region. Okay. If we tested it, we would have 0 is greater than negative 2, which we learned is true. 0, 0 is a solution. What about one of those points I put down? What about this one right there? 2, negative 2.
Yeah.
Not a solution on the dashed line. Makes a invalid inequality. Okay, that's not a solution. Right above it is 2, negative 1. 2, negative 1. And anything else in that shaded region, maybe something way over there. What about 11, 0? Is that in the region?
Yes.
Has to be, right? We see it's going down and getting a larger shaded region over here.
Wait, why do you have a different?
All right, the next example here, we had to solve for y first, because this one's in standard form. Can't graph this one until we get the y by itself. So over here, we looked at, the first thing was to do was subtract x from both sides, so that we'd have negative 2y, still have the greater than or equal to, now negative x minus 2. Last thing there, to get the y by itself to become graph ready, we divide by -2 on everything. And remember, we just divided by a negative. We have to flip the inequality the other direction. So our slope-intercept form will be y is now less than equal to. We go over here to look at the slope. We see a -1 over -2. It'll become a positive 1/2 of x. And then -2 over -2 becomes positive 1 for the intercept. So there's our y-intercept. We plot the y-intercept, 0, 1. And then our slope is 1 over 2. So we're going to go up 1 and over 2 to that point there. And then now we look at what kind of boundary we should draw. We see we have a solid boundary. That's because we have an equal to. Remember, equal to will always make a solid line, because all the points on this line are exactly equal to -2. All right, so once we have that, we know it's a solid boundary. And now we look at the shading. It's a less than, so we see we're going to shade below. That's what our graph shows here. We're shading below the boundary, the solid boundary line. So all of this blue area is the shaded region. All right, for the possible solutions on this graph, we can use those points up there. If we wanted to use that point on the line, what is that, 2, 2? That would be a valid point. It would be the exact answer. You would have, let's see, 2 minus 2 times 2. Well, that's going to be 2 minus 4, which is -2. And -2 would be equal to -2. All right, so those are the equal to points. And then any other points, maybe like 5, 0, that's in the shaded region. Or another one, maybe like 0, -5. Any points in the shaded region or on the solid boundary line. Let's go to the example 5. See, I already have the graphs there, but let me explain how we get the graphs. Actually, let's go ahead and practice the other way of graphing, and that is the intercept method. So we found, we did this before, where we found the x-intercept, which we had a 0y value, and we found the y-intercept, which had a 0x value. So let's go ahead and practice that. So let's go do the x-intercept first. X, we'll put in 0 for y. We see the x will be -2. And the y-intercept will be exactly the same thing. Put in 0 for x, and y is -2. So there is our 2 points, -2, 0, and 0, -2. And then we draw the boundary through there. Again, the boundary will be, we don't have an equal to, so we see that's going to be a dash boundary. And that's what our graph shows down below, a dash boundary. And we see it's a greater than. But now this is in the standard form, so we can't take the sign and do that. So let's use our other method and test 0, 0. So we're going to test 0, 0. And we're going to plug in zeros for x and y and see that we would get 0 is greater than -2, which is true. And that's why it's right there in the shaded region. And so we would know to shade everything above this boundary because it would include the 0, 0 test points. For the last example over there, example number 6, this is not going to be so easy for intercepts because 3 will go into 9, but the 2 won't divide in evenly. So we are stuck doing the slope-intercept method, which always works, so don't think it's a bad way. Okay, so we're going to subtract 2x first from both sides. So that would be now 3y less than equal to -2x plus 9. Last thing to do to get the 9 by itself, I'm sorry, the y by itself, is to divide by 3. It's positive 3, so we don't have to flip anything. The inequality will stay the same. So it will be still y less than equal to, reduce the slope, can't reduce it, -2/3 of x. And then 9 over 3 becomes the intercept of positive 3. So there's our y-intercept. Plot that, 0, 3. So you can see that's on my graph right there already. And then now we're going to go down 2 and to the right 3. Down 2 to the right 3 puts me on that point right there. Okay, and I could use those points for my solutions because, again, they're on the equal to a solid line. And then, speaking of our solid line, we have to write that down. Our solid line comes from our equal to part here, so we know it's going to be a solid, and we will be shading below because it's a less than. So all the points down here below the boundary. This is why this area is shaded in. All right, may the math be with you.